All right, friends and neighbors, welcome back to another networking video. This week we are doing finally iBGP, and it's been quite an interesting journey to get to this particular one, and I'll explain that later on in this video. But here we go, eBGP versus iBGP. Now let's get some definitions out of the way, right? It's pretty straightforward, but from RFC 4272, the BGP4 RFC, we now know that eBGP is external and iBGP is internal. And so what that means is that you're communicating with a different kind of peer. And so the peers are going to be external if it's a different AS. They're internal peers if they're the same AS. All right, pretty straightforward. Now, BGP topologies, if you have an AS and you're going to have internal BGP peers, what usually ends up happening is that your internal topology is built using an IGP. So it's not just that you set up BGP internally, although you could if you had a large enough network. We actually see BGP being used all over the place for things that, maybe for which it was never intended, but that's a story for another day. So you usually run an interior protocol like eIGRP, and in this case, I ran OSPF, and then you set up your internal peers. All right, so there we go. So that's some definitions from RFC 4271. Now, here's some language from the RFCs, and maybe we'll just go through it real quick, just to sort of get our minds in the right place. If a particular AS has multiple BGP speakers and is providing transit services for other ASs. Now, what that means is that if we remember that the whole point of BGP is to set up a connectivity graph for networks that are reachable via ASs. So that probably means that there's ASs in the middle. And so those ASs in the middle that are interconnecting other ASs, well, those are providing transit services. You could call them a transit AS. So what that means is that now you've got this internal set of networks, and we want to provide what we call a consistent view, right? A stable view of what that topology looks like inside that transit AS. And the way that we do that is with an IGP. And for the purposes of this document, the RFC, it is assumed that a consistent view of the routes exterior to the AS is provided by having all BGP speakers within the AS maintain iBGP with each other. Oh, okay. So this is really about transit ASs and establishing, what your topology or what your connectivity is inside your AS, so that you can feed and connect each other to all of the other external ASs that you might have. And then guess what? We normally do that with a mesh topology between iBGP speakers. Hang on a sec. Mesh topologies? So the language of a mesh topology, right? So if you're looking at the Cisco docs like I was, then you come across mesh topologies all over the place. But the word mesh does not appear in RFC 4271 at all. So how would you know that? Well, one of the companion documents that you should read if you're trying to get a handle on, your BGP topology is RFC 4456, previously 2796. And so right in the preamble, in the introduction of that RFC, it says, typically all BGP speakers within a single AS must be fully meshed so that any external routing information must be redistributed to all of the routers within that AS. Oh, okay. So the RFC recommends that you should have a mesh topology. And that's the Cisco documentation as well. So in the upper right here, I got this right from the Cisco docs. Here we've got a mesh topology, meaning that all of the routers are connected to all of the other routers inside that autonomous system. Now, if you've been doing routing for any period of time, you know that this is fraught with danger. I'm going to use that word later on for another reason. But this is dangerous. When you have a routed topology that's in a loop, you can have problems. And, well, heck, let's start talking about those. When we have a mesh topology, or so in a 3-router mesh topology, that's pretty easy. Just everybody's connected sort of in loops. But if you had a 4-router, a 5-router, a 6-router, then it gets really, really complicated. You're using up interfaces, and there's lots and lots of capability or possibilities of loops. And the problem with loops is that if one router goes down, the source of the information or the source of the route goes down. If you're in a looped topology, the other routers might believe that that network is still available. And for this reason, we do things like split horizon in routing protocols to avoid loop. There are also a number of other routing techniques that we use, such as null routing. We can do poisoning. We can do count to infinity in the case of RIP. So there's lots of techniques that we use to ensure that loops don't cause problems. And so BGP has a similar one. So what that means is that iBGP speakers do not advertise all of the routes to each other. All right, so mesh doesn't scale very well. We have problems with loops. How do we ensure that we get all of the networks? And that brings us to RFC 4456, which offers this alternative to a mesh topology, which is something called a route reflector. And so in this case, we advertise learned routes to some BGP peers. And this language is also the language that we find in the Cisco documentation. Okay, so that's what this link is down here. If you look up configuring iBGP on Cisco's, you'll start to see that. Okay, so let's go over a couple of rules. When you have iBGP, so when you set up an eBGP topology, it's fairly straightforward, right? The router is given an autonomous system number, and then we do the open, the update, the keep alive. But when you're an iBGP speaker, there's a couple of things that are a little bit different. First of all, that iBGP speaker is not originating the route anymore. Well, it is to an internal peer, but it's not the one that said, "Hey, listen, I have this path to the destination," and so the AS path attribute is not modified. That iBGP speaker is not the source of all information with regard to the externally advertised route. Now, when the internal speaker is the originator of the route, then what we do is we empty the AS path, because it doesn't make any sense to have a path to, or an AS path to a route that's internal to your AS, right? It's just, you're just going to be given the forwarding. And because we know who our internal peers are, we know that this internal route is going to be internal versus external. So if you're an external route, right, you're going to get an autonomous system number on it, you're going to get an AS path, and you're going to get the proper forwarding router IP address or next hop. If it's internal, we're going to zero out some of that information because, well, it's inside this AS, there is no AS path to get there. Well, here's the topology that I wanted to set up for you in Packet Tracer. And so it was, and actually I was going to do a much larger topology, but as I ran into issue after issue after issue, and I'll lay some of those out for you later on, the topology finally got to about this size here. And here is the reason that I didn't do this in Packet Tracer and why I ended up going to the lab. Watch this. So here is a packet tracer topology, and you can see that we've got a bunch of AS numbers here. Now this is not the example in the slides. This is an example of why you can't do this in packet tracer. Okay, so just really quick, right? We've got this router that's connected to the 2 and the 3 networks here, and the idea was that this right here would be where I would set up, iBGP. Okay. Now, if I go to this router right here, and we can see that this is the 2 and the 3, so I'll show you quickly the configuration. All right, so we've got our loopback, and we know that BGP likes to use the loopback as the BGP ID. Here we've got the 2 and the 3, and then I started on the BGP configuration. Now this part of it is pretty straightforward. This router has an autonomous system number of 20,000, and then over here we have the 10,000. Well, what you would do is you would say, well, I want this to be my internal peer. And so what I'm going to do is say, all right, we'll say router BGP 20,000 in this case. And then I'm going to say neighbor 3.3.3. I think it was 254. Yep. And then it'll be a remote AS. And then what would I do? Well, this would be an iBGP peer or an internal peer. So I would use the same AS number, 20,000. Oh no, Cisco Packet Tracer does not support internal BGP in this version. In fact, this goes back a long time. Lots of folks have been asking for this particular feature to be built in, but it's not. So here endeth our journey in Packet Tracer and BGP. So we're going to just close this right now. So in the lab, I swapped the topology just a little bit to make my life a little easier. And because, I was limited on the amount of equipment that I had or wanted to work with, what I did internally is I created some VLANs and ran OSPF here. And then you can see my addressing changed a little bit. I went with the 2net, the 3net, variations on the 4net, the 5net, and the 6net. So what would happen, the very straightforward part of this is that eBGP working outside here would quickly discover the autonomous systems and the networks that are connected via those autonomous systems. And internally, we would learn the OSPF routes very easily because, well, it's just an IGP. And the challenge then became, with all of these being internal speakers, to get the route reflection set up. And so it's a command that you use to just say, this is who I'm going to reflect routes to, as described in the Cisco docs and as described in the RFC. But anyway, here's our topology. Now, the red arrows here indicate just where I was capturing traffic so that I could see things happening. And what you're looking for are those updates, and you're looking for, especially internally, you're looking for the updates that have those characteristics of being an internal route. And I'll show you an example of one of those, and then I'll show you the final routing table. So here is an actual capture from the network. And so I've gotten, a config from part of the network, and then I've got a capture from part of the network here too. So let's begin with this configuration. We can see based on the networks that are here that not only is this part of that topology, the internal BGP topology, but we can sort of guess where it is from the set of networks that we're advertising here. We can also see that the peers are 41 and 42. So the peers are on that left-hand side of the topology, and the networks are on the right-hand side because this is the router on the right-hand side. Now, this particular packet is from that left-hand router sending a BGP message to its peers inside the AS. How do we know that? Well, we know where the 3net is. That was on that left-hand side. And the 41 net is also a directly connected network here. Now, what makes this an iBGP or an internal peer generated packet is that we can see that the AS path here is empty. Why? Because this is inside an AS. We're not going to add anything to this path. The AS path is not going to be either appended to or changed by this particular router. And we can see that for the internal routes, right, the router is using itself as the forwarding interface. So this indicates that this particular message is from an iBGP peer or an internal peer. Okay, let's take a look at the routing table. Now this is a routing table again from that router on the right, the one that we saw the configuration for. So first up, we can see that we've got all of these OSPF and directly connected routes. This is the internal topology of the autonomous system. And so this was the IGP that I was running to learn about all of these different networks. And you can see them all here, the 41, 42, 43, 44. And then I've got a directly connected network for the 5net. And this is also another indication of where we are in the topology. All right, now all of these other routes were learned via BGP. Let's take a look at this one right here, the 6net. So this was the network all the way to the right in the topology, if you want to go back and look at that. And take a look at the admin distance. It is 20. So the admin distance here is 20, which tells us that it's an eBGP learned route. These other two, the 2 and the 3, were sourced from or propagated by an internal peer. That means iBGP, and the admin distance for iBGP is much higher, 200. So the externally learned routes or the external peer source routes are much preferable or much preferred in BGP, and the internal routes are not. Now, this particular build was fraught with challenges. Not only is it finals week here at RIT, and I'm doing all this grading, but we ran into that packet tracer problem with BGP. And so while this isn't me, that's definitely what I felt like in trying to get this build done. The other issue is that when you are trying to get iBGP supported by your Cisco gear, make sure that they have the same versions, because there are actually different mechanisms used to get iBGP speakers to talk to each other depending on the version and the hardware. So make sure that you've got compatibility, make sure that you have an iOS version that's willing to use the commands that you want to use. And in the end, this is what I use to get the route reflection and the routes propagated. The neighbor IP address, and that it was going to be a route reflector client. Well, that finally gets us through BGP, and I think we polished off iBGP here. Thanks for watching. Thanks for listening. Like and subscribe if I helped. And whether you're doing iBGP or eBGP, may those packets always reach their destinations, even if that admin distance is 200.